Can I start? Okay. Hello to everyone. I am Stevan Durdevic from University of Montenegro. I am the leader of Montenegro team. The theme of my lecture is the quantum Hall effect. It's not proper for high school pupils. Because that I will be very short. It is not only one reason for that. I think that you have too much lectures in this period. The quantum Hall effect, the classical Hall effect is the first discovered in classical dynamical systems, and then in 1980s, in 20th century, we discovered quantum Hall effect, and we saw that exist two kinds of quantum Hall effect: integer quantum Hall effect and fractional one. The classical Hall effect was discovered in 1879 by Edwin Hall. It is a simple consequence of motion of charged particles in a magnetic field. The classical Hall effect is explained by Lorentz force. I hope that you know what is a Lorentz force. When you have a charged particle in a magnetic field and he has some velocity, the Lorentz force is proportional with cross product of this velocity of magnetic field vector. This is the system. If you have some conductor in magnetic field B, the carrier of charge and current are electrons in metal usually, and when we have a current in that conductor in magnetic field, the electrons go to one side of that conductor, and because that we get a perpendicular difference in potentials of two sides of a conductor, and we have a plus side and minus side. The more electrons will be on this side with dominantly negative charge, and in that direction we have some voltage that's called Hall voltage. And this is the essential of classical quantum Hall effect. Okay, the definition of Hall resistance is the Hall voltage over current through this conductor, this current, and Hall resistivity. Hall resistivity is 1 over Hall conductivity, and here you can see the Ohm's law in local sense. For two-dimensional electron systems like our metal conductors, the resistivity is a tensor. I know you don't know what is a tensor, but this diagonal element in that matrix is usually resistivity, and elements out the diagonal are Hall resistivity. Here I have some film about Hall effect, classical Hall effect. Is it possible to start my film? Yes, video. Ah, okay. Mm. Here, where is the video? Is that here in the video?
Ah, no.
Where is the video?
On my computer. Okay.
Okay. I'm sorry, my video, I don't put on that computer. Okay, it's classical story about Hall effect that I tell. The dependence of Hall resistivity in classical case is linear. The dependence of the Hall resistivity of magnetic field. This is the usual resistivity, and this is the Hall resistivity. And in, I think, 1980, Klaus von Klitzin discovered some strange things. The dependence of Hall resistivity is not, of magnetic field is not a linear, but this dependence have plateaus. And plateaus emerge in very special numbers, very special values of magnetic field. This picture shows integer quantum Hall effect. And this means that we have some quantization, and origin of that quantization is of quantization of energy levels of two-dimensional electron system in a magnetic field. This quantization, this energy levels are called Landau levels. And I don't talk about mathematical approach to that because I think it's not proper for high school students. And what mean this integer numbers? For some value of magnetic field, we have exactly integer number in some region of magnetic field. This number expresses how many Landau levels are filled, fully filled. The degeneracy of Landau levels is extremely high. Oh, I'm sorry, this in Serbian. I saw that. Klaus von Klitzin awarded with Nobel Prize for discovery of quantum Hall effect. I think the birthday of quantum Hall effect in laboratory is February the 5th in 1980. And Tsui and Stormer discovered the fractional quantum Hall effect in 1982. It's this phenomena is very strange for theoretical physics and very interesting for theoretical physicists because for fractional quantum Hall effect we don't have a very good explanation, very good theoretical explanation. Because what is the fractional Hall effect? In integer Hall effect you had integer numbers or integer a number of Landau levels are filled. But in fractional Hall effect this number is called the filling factor. In fractional quantum Hall effect the filling factor is is like a fraction. And Zhang gave some theory in his papers from 1988, 89 and 1990. But for fractions, for fractional filling factors with neparni, odd denominator. But for even denominator, we don't have a good explanation. Now, in fractional quantum Hall systems or fractional quantum Hall regime, we have some pairing mechanisms, and the fractional quantum systems have some superfluidity characteristics, and in the same time you have a Meissner effect. Meissner effect is mainly characteristic for superconductivity, because superconductors tends to push out magnetic field in the sample, superconducting sample. It's very strange for fractional quantum Hall effect, because the pairing mechanism in superconductors is in BCS theory is electron-phonon interactions, and we have Cooper pairs. But in fractional Hall systems, we have many channels of pairing. And Haldane, I think in 1986, was show some mathematical method for explanation pairing mechanism in fractional quantum Hall regime with some mathematical object to project all Hamiltonian of fractional quantum Hall system to one Landau level, and they get some pseudo potentials which called Haldane's pseudo potentials. It's mathematically very hard to do for you, and I don't put any of that in my presentation. But you know, you can see for the quantum Hall effect, it is needed to have a very strong magnetic field, about 10 Teslas. It's very strong. I think that in laboratory we can take a maximum of about 13 Tesla, I think. Professor, I think about 13. It's very a strong magnetic field and a very low temperature, about 1 Kelvin. And one of strange facts is the system must be two-dimensional, not in three-dimensional. Can emerge quantum Hall effect. Okay. Mainly I work in solid-state physics. This is a part of solid-state physics. And we have a problem with the name of that field, solid-state physics. You assume to have a solid, but the two-dimensional electron system is usually two-dimensional electron gas, or superfluids are liquids, and we called our field condensed matter physics, and essentially of that is condensation, quantum condensation, and superconductors, superfluids, systems like this have some quantum condensation, and you can use quantum statistical mechanics for theoretical approach to this phenomena. And because I didn't understand Kostas Vourlias in his mail to make a lecture, I firstly prepared in very high level my lecture, and this I prepare now when I come in the morning. Okay, I am finished, and thank you for attention. And I can tell you that many things in physics are super, like supersymmetry, superconductors, super fluid, super string, and every physics is super. Thank you. I think that Professor Zmarzek is next.